Everyone, today I'd like to talk a bit about atopile, which is a compiler for electronics that we've been working on for the past few months. And to make that conversation a bit more exciting, I'm thinking we're going to talk about it by talking about a real electronics project that will serve as an example of what we can use atopile for. Before diving into the compiler, let's quickly talk about this project. Basically, the goal for this project is to build a kit so that kids can learn about logic gates. And so it consists basically of a box that looks like this. The box is not complete, but you would have two buttons right here and an LED right here. This PCB would go inside the box. On the PCB, you have two buttons here, the RGB LED right there. A kid should be able to place those cards on top of the box. And by placing those cards, it should turn on the microcontroller that is inside the enclosure, and it should program it so that those two buttons react in the same way that is depicted by the logic gate that is on the card. And obviously we should be able to assemble multiple cards. So I have this was the AND gate, this is another one, this is just a wire, for example, that covers one of the buttons. And so this is how roughly the project is organized. And there's a few problems with this first version of the project, namely the fact that those cards are very hard to assemble on top of the box. And secondly, that I'm not a big fan of those connectors, like those pin connectors that I chose, because again, it makes the assembly very hard. So the goal of today will be to switch out those few components and replace them with something that is more suited. First step will be to redesign the shape of the enclosure. And the goal is to be able to take some of those cards, push them onto the enclosure, and then slide them sideways a bit, and with pogo pins that push back up onto this card. And then we should be able to remove it again by pushing down, sliding sideways, and pulling it out again. So let's look a bit at how this project is organized. Everything is version controlled on GitHub. You can find the project here under my account logic card. You can see an image of how the project looks like when it's fully assembled. And all the code that defines this project is contained in this repository. And so that's when we come back now to the compiler, because this project was generated with atopile. So what is atopile actually? Atopile is a compiler for electronics. The goal is to create a tool that enables you to describe electronics with code instead of using the conventional schematics. So here you have an example of how this code would look like. This is the code that describes this PCB, so the logic card. You can see how we can import some components at the top of the project. And then we start splitting our project into multiple modules. Each module is a reusable block, like a class would be an analogy in the software world. And we can create instances of those classes. So for example, here we imported the resistor right there, and we're making an instance of the resistor in that location. Okay, so let's dive a bit into what we want to do today. So as I said, we do want to remove those pin headers that I was using before. So actually, we can go right ahead and delete, I guess, all of this, because we're not going to be using it anymore. And I want to replace those connectors with some kind of pogo pin like this one. So I found this one on GLC PCB, and we're going to go ahead and install this. To install this component, we can come back to our VS Code environment. Let me increase the size of the screen so we can actually see what's going on. And the way to install this, we can simply, in a command line, say atto install --glc PCB, and then the name, the part number of the component. So what's going to happen here, it's going to pull automatically the footprint for the pin and create a component for us, as you can see right here. So perfect. Now we're going to import this component into our main project. So if we go here to the top, we're going to import pogo pin. Just like that. So now we have this component imported into the main project. So let's create some instances of that component below. So we're going to create those instances inside the logic card, because the logic card is what represents this PCB, and it's actually the PCB that we will compile, it's the module that we will compile to obtain this PCB. So if we go a bit lower, you can see that here we were previously using this pin connector, and I want to replace it. So we're going to remove it from here, like that, and we're going to remove it from here as well. Actually, let's skip this for the minute. Let's create a few instances of the pogo pin. Let's call it pogo1 equals new, and that's correct. So we're going to create, so just to explain what's going on here, my goal will be to be able to place multiple cards, and previously I was pulling down each one of those signals depending on which card I was assembling. But I realized that instead of doing that, I can use a binary code, and this should allow me to reduce the number of pins that I'm going to have on going from the bottom PCB to the top one. And so I'm thinking that I'm going to use 3 pins, and this should give me a total of 8 possible solutions. So let's create the second one, and we're going to create a third one like this. Perfect. And we're actually going to call it maybe program, because those are the ones that are going to be used to program which card is installed on top. Okay, so we can remove those few components. I was using this before. We can remove this as well. We're not going to have any ground sent to the top card, I think. And so here we simply replace those few components with the ones that we just created. Let's check what the signal name is. It's called _1. I'm not sure I like that. I'm gonna call it in instead, just like that. And here we want to connect the number 2, and here the number 3. Perfect. So now those 3 pogo pins are connected to the microcontroller, and they will later be sent up to the cards that are installed on top of the microcontroller. So actually, if we think about it, those cards currently have those connectors that are installed, and let's try to find where those cards are defined. So the way this works is that in this case, we are utilizing subclassing. So what subclassing is, it's a way to create, let's say, an abstract representation of what a PCB might become. And then by subclassing it, we can add elements to it. And that's very useful if you know that you're going to have certain parts of your circuit or certain PCBs that all have the same connectedness information or same components. And then by subclassing it, you can further define it into multiple directions. And so here, that's exactly what we want to do, because we know that the program card doesn't have those connections that we had before, but instead it's going to have a few pads. And so we're going to say pogo pad program pogo pad 1 program, like this, equals new. And here we're not gonna use the same pogo pin. Obviously, we're gonna create a pad. I'm not sure exactly how I'm gonna design this for the moment, but we're gonna call it pogo pad. The reason we use this notation with capitals at the front is because those are class definitions. So we can copy that line, and we're going to have it 3 times, because for each pin we need a pad on the card that comes on the top. Perfect, we have those 3. You will notice that this pogo pad is actually not defined, so let's maybe define it in here. I think it makes sense to do that over there. Pogo pad. And in there, we're gonna say, we don't know the MPN yet. So I'm gonna call it unknown. Perfect. And we're gonna create a signal in as well. And we're gonna connect that to pin 1. Again, here we don't know what footprint we're gonna use. So for the moment, I'm just using that. I can actually copy this one. I can copy it over and maybe just add a to-do that I need to switch this footprint. There we go, perfect. And let's remember that we need to import this pogo pin over. And I want to change the name pogo pin pad but atto. Let's call it like that instead. I think it's more suited. Whoops. Perfect. Okay, I think that will work. So now we have the 3 pads that are being sent up to those program cards, but with those alone, we wouldn't be able to program the microcontroller. We'll need another pad that is at a high voltage, 3.3 for example, and by shorting each one of those program pads to one of the 3.3 volt pad, we can send a signal to the microcontroller and program it in the proper way. So let's create it here. So v3 let's call it pogo pad 3v3 equals new pogo pad. Perfect. So now we have those 4 pads. That's everything we need for the moment. So as you can see here, now we are subclassing the program card into the AND card, the OR card, or the wire. So what I want to do is that for the wire card, I will simply connect one of the pads. So the 3v3 dot in, and we'll connect this one with the pogo pad 1 program in. Perfect. We'll copy this line and we will replace it here and here. Perfect. And in this case, I'm going to use the pad number 2, and in this case, the pad number 3, just like that. So now each of those cards is going to be programmed differently. So I hope with this example, you can kind of see some of the power of atopile and the description of hardware using code. It's trivial to subclass elements and further specify them in a relatively complex chain. I just realized that the last thing I want to do is change those pull-up resistors, and I'm going to replace them with pull-down resistor instead. So I'm going to remove 2 of them because we previously had, I think we had 5 for each one of the pins. But now that we're going only to 3 pins, we only need 3, and we need to change the way they are connected. So the way to do that is, first of all, I want to change their name. So I'm going to call it our pad 1 here. That's good. Command D to select all the things with the same name on a Mac. That's pretty useful. Okay. And lastly here, our pad _3. Perfect. And so now we said we wanted to change the way they're connected. So in this case, we will put the pogo pin 1, pogo pin 2, and pogo pin 3. Whoops. There we go. That should work out, and instead of connecting to, instead of pulling up, we will pull down, because I'm thinking that the card will be pulling up those lines. Perfect, so now we can try building the project, so compiling the project. And again, this is a new concept in electronics. Usually you wouldn't compile a schematic, but in this case, because we have more abstract representations of how the circuit is connected, we do need to ask the compiler to go and read this code and generate the netlist for us. Once the netlist is generated, we can just route a PCB like we usually would on KiCad or other programs as well. So we call atto build, and as you see, this builds a project, and we have a few errors. So let's see what's going on. So in this case, it tells us that it couldn't find selector in, and that kind of makes sense because we deleted the selector. So I probably forgot to remove it from a few locations. Let's see what's going on. Oh yes. So what was happening before is that I was sending the battery voltage up to the cards and back down into the microcontroller card, and this is how we would turn on the circuit. But I don't want to do this anymore. I think I just want to add a MOSFET to the microcontroller card on the low side. And then once we install the card, the gate of the MOSFET is going to be connected to the top card, and that should turn on the circuit. So I will do this later, but for the moment, let's just remove this whole section of the circuit. Let's try to build again. Another issue, and indeed, this is not the name of those pads. We want to change this to in, and in. Okay, that should now work. Okay, last error. So in this case, it tells us that it couldn't find this reference. I don't remember what this component was. Oh yes, that was on the card. We had 2 of those connectors. I forgot to remove the second one. So let's just remove this completely from the project. We don't need it anymore. Great, we can try building. And so let's look at the outputs we have here. So because we're building 4 cards, we have 4 different outputs. So one is here, one is here, one is here, and the last one is here. We might have to clean this up because it's difficult to see all of them. You can also obviously compile just one of the cards. And this is the BOM. So here you see all your components. It selected some components automatically for you for the resistors and the capacitors, and they are grouped together for the components that have the same values. This is just a table that shows you the name of your variable in the atopile project and the name of the designator that it's going to take when you will route your PCB. It's pretty handy to have this because as you jump from your layout back to your atopile project, you can see what's the correspondence between those two elements. Okay, the last thing I want to show is the fact that we can now use Git for this project. So if you have never used Git, Git is an awesome versioning control tool that is commonly used in the world of software. And because we are now describing our circuits using code, we can use Git in the world of the electronics. So this is obviously very exciting. So let's see what's going on here. Apparently I changed a lot of things. For the moment, I just want to push the change that I just made. So we will say git add this one, this file, and I also want to add the one that I just added, which is the pogo pin pad here. So we're adding those two. Let's see if that's properly executed. It is. Perfect, and we will commit this. There we go. And we can push that back to the project. This is now pushed back to GitHub, so it's available to everyone. Okay, that's it for this video. In the next one, we will go into how we will take this project and start generating the layout. And finally, we will look into how to take this project and generate build outputs automatically in CI on GitHub. But we're probably going to split all of this into 2 additional videos. So see you soon. Thanks for watching. Bye.